We're talking about transformations of quadratic functions and focusing on standard form. So standard form of the quadratic function is f of x, or y equals ax squared plus bx plus c. So the ax squared, that's called the quadratic term because the x is squared. The bx is the linear term because we're used to seeing the b as the slope there if we had y equals mx plus b. And c is the constant term because there's no variable associated with it. It's just by itself, just right there. The parent function, or the base function of the quadratic, is y equals x squared. There's no a value, and the b and c values are 0. The scale factor of the parabola, that's the shape that the quadratic function makes, is a parabola, and we'll look at that in a second, has a vertical stretch and a vertical shrink. As a gets larger, the graph gets narrower or rises faster, and we'll take a look at that example. So a cannot be 0. If a were 0 here, then this first term would drop out, and we'd just be left with a linear equation, bx plus c. So a cannot be 0. If the a is less than 0, that means the a value is negative, then it's going to be concave down. If the a value is greater than 0, it's going to be concave up. And then depending on the size of the a value, so if it's between 0 and 1, basically we're looking at a fraction or a decimal, the parabola will be very wide. Or if the a value is 1, it's just going to take the shape of the parent function. And if the absolute value of the a value is greater than 1, then it will be very narrow. These are the equations that we'll have to use to figure out what that will be. And in this case, we have the equation for the line of symmetry, x equals negative b over 2a. We'll have to use that. And the y-intercept of 0, c. So whatever the c value is by itself, that's where the graph is going to intersect the y-axis. We can also calculate the vertex using the same equation that we did earlier. So let's take a look at a couple examples. Here we have the parent function. This is what a parabola looks like. So y equals x squared, that's the parent function. And we can see that we have the intersection at 0, 0. And then basically, as we substitute values in, what happens? So if we substitute 1 in for this, 1 squared. So substitute 1 in for x, 1 squared is 1. So 1, 1. If we substitute 2 in for x, 2 squared, go over 2. 2 squared is 4. So we get the point 2, 4, and that continues. The other thing that we notice is that this graph is symmetric over the line that goes through the vertex. The vertex is right here. That's the point of inflection. That's where the graph changes. So if I count over 1, 2, that gets me to this point, which is 2, 4. If I go the other way, 1, 2, that takes me to the point negative 2, 4. So the y value, the height stays the same, but now we're 2 units over to the left instead of 2 units over to the right. Now we talked about the a value. The a value is the value that's in front of the x squared variable. So in this case, we have a 2. In this case, we have an understood 1. So what's going to happen here is we can take a look. We can see that this graph is a little bit more narrow. So basically what it does is it takes all of the values and all the y values and multiplies it by 2. So where we had the point 1, 1, the x value is not going to change, but the y value is. So what is 1 multiplied by 2? 1 multiplied by 2 is just that. is itself. It's 2. So we have the point right here, 1, 2. So everything basically gets doubled. Now we can take a look at, well, what happens if it becomes 1/2? So 2 made it narrower, so it's getting very tall very fast, and it's getting a little bit closer to the y-axis. What happens if we put in 1/2? So 1/2 for the a value, we can see that the graph got a little bit wider. It got a little bit further away from the y-axis. And if we go over 1, up 1, we still have that 0.11, right? That's the original function. Well, now we're multiplying by 1/2. So what's 1/2 times 1? It's 1/2. So 1, comma, 0.5, and that's what our value is there for that graph. And basically every function, every part is divided by 2. So here we had the 0.24. What's 4 divided by 2? 4 divided by 2 is 2. And so we have the point 2, comma 2. So I'm going to shut those 2 off. Now we have another function here. The thing that I really want to pay attention to is this 4 right here, this -4. That is going to be the point where this graph crosses the y-axis. So down here at -4 is where this graph is going to cross that axis. And there we can see right there at 0, -4, that is where this purple graph crosses the y-axis, because that is always going to be the y-intercept. It doesn't matter. I can change this to +4. And whatever that constant term is, that's always going to be where the graph crosses the y-axis. Last thing we'll talk about before we get into some specific examples, here we have the -2. What that -2 value does is, so far, all of these graphs have opened up, like basically like a cup that you're going to drink out of. So these are opening up. That's called concave up, right? So it's opening up. When we put that -a value on the quadratic term, what that does is it makes the graph flip over or reflect over the x-axis. And so the -a value makes sure that the graph opens down. So we talked about a few of these things. If the a value is less than 0, meaning negative, it's concave down. So we saw that that makes the graph look upside down. If the a value is greater than 0, then it's concave up. And then we talked about the a value, how it makes the graph wider if it's a fraction, or it makes it more narrow if it's greater than 1. And we also talked about the c value always being the y-intercept.